Hello. Today's video is going to be about controlling the water level in a tank, actually in two tanks. This is a problem that I saw on LinkedIn in one of the engineering forums. There was a student that had a problem where he had to control a cascaded system where there was a pump that would pump water into a tank one, and in the bottom of that tank one there was a valve or orifice that was fixed, and the water would flow out of that valve or orifice into tank two, and the trick was to control the level in tank two. There was some debate as to whether or not the system was even controllable, although to me it seemed obvious that it was controllable because you could almost think of it as each tank having a time constant. But the time constant isn't really constant, but we'll get to that later. So to start with, I was telling the student that I wouldn't even give him a passing grade unless he could write the differential equations for the two tanks, because at first it might seem unnecessary, but you will see that later on in this video that it's going to be very important, because what I'm going to try to do is make it so that it's more than just an exercise in learning how to control the level in a tank. Obviously, most people would just fiddle around with PID gains until they got it to go. But you don't go to college to learn how to fiddle PID gains. Obviously, a monkey can do that, or a million monkeys can do it and eventually get it tuned. When you go to college, you want to learn something. So that's the whole idea of this video. So to begin with, let's write the equation for the two tanks. The top tank, tank 1, flows into tank 2, and Y is the water level, and QP, so T, that's the pump flow as a function of time. And if you take the pump flow and divide it by the area or surface area of the tank, that will be that will cause the surface level to go up or down, or the level of the tank to go up and down. And then also the tank, the water in the tank is going to flow out, and we're going to make an assumption to begin with, which isn't right, but we're going to make an assumption to begin with that the water is going to flow out proportional to the elevation of the water, or the height head of the water in the tank. So this is the flow constant, and if you divide the flow constant by the area, you get how the level is going to change as a time constant. And then we have somewhat the same equation here for tank 2, only you have tank 1 supplying tank 2, but other than that, the two equations are the same. I'm going to assume that I got a gain and a time constant for tank 1 and a gain and time constant for tank 2. Right now, I'm using the word time constant loosely. But let's continue on. Scroll down here a bit. Okay. Gotta scroll. Okay. So this is the plant, or the open loop transfer function for the first tank. Again, I'm assuming that everything is constant, and I have a proportional gain to control it. Now, why am I using a proportional gain only? Well, the simple answer is that's all that's required, because there's basically two tanks with a time constant. You need to have a gain for each time constant, plus you need to have an integrator just to reduce the error to 0 on the last tank. So we have a proportional gain only for the first tank and a PI controller for the second tank. So we're going to have a cascaded control system where the second tank's PI is going to set the level for the first tank, and thereby controlling the water flow into the second tank and controlling the level. So this is the closed loop transfer function for the first tank. And then what we need to do is add that into the second tank. So let's just talk about the first tank here. This is the PI, this is the controller gain for the first tank. This is again, the open loop gain for the first tank and the time constant. And this is the equation substituting for the closed loop control, substituting these two equations into this equation, I get this. If I simplify it, this is what I get. Then I got to insert that into the transfer function for the second tank. So we have the controller for the second tank here and here. Now I'm only using the proportional gain in the feedback path. In other words, I'm not using a PI controller, really. I'm using an I minus P, where the proportional gain is only acting on the change in the water level in the second tank. This is the transfer function for the first tank, and then this is again the open loop transfer function for the second tank. And this is the complete closed loop transfer function now for the second tank. And if I simplify that so I have a characteristic equation in the denominator, this is what I get. And it looks awfully messy because there are 4 variables. The 2 gains and the 2 type constants. Well, actually there's 4 gains here if you add the controller gains. So to control this, what we want to do is we want to pick a desired closed loop transfer function or a characteristic equation. And I could use 3 real poles and then place them at -1 over the time constant. This is the closed loop time constant. But what I want to do is try the Butterworth coefficients. So in that case, I replace these 3's with a 2. You'll find that this is the coefficients that you'd use for a third order Butterworth filter. And then the next trick is to equate the coefficients for each power of s, like I've done in the other videos. What's different about this one is that we have coefficients for the third power of s, and there's nothing for the 0 power of s. So what I have to do up here is I have to divide the coefficients for the characteristic equation by this term here to get a 1 in the denominator. So this is the coefficients for the third power of s, the second power of s, and the first power of s. And if I solve, I get the controller gain for the for the P gain for the first tank up here, and I get the controller gain and the integrator time constant for the second tank here and here. And I'm just going to make a function where I calculate the gains as a function of the gains in the time constants and the closed loop time constant, because I'm going to be using this function a few times. I'm going to simulate 20 minutes. Update period is going to be in seconds, but I'm going to define it as 1/60th of a second or minute. And I'm going to change the set point a few times. I've got disturbance where I pour in 2 cubic meters per minute into the second tank, and we'll see how that reacts. Now, up to this point, I have assumed that all the gains and all the time constants are really constant. And one of the assumptions that people make, well, that's a poor assumption in a lot of cases, especially on tank control. You can see that on a normal hydraulic system, the flow through an orifice or a valve is proportional to the square root of the pressure drop across it, which is going to be proportional to the head in the case of, or elevation of the fluid in the case of our tanks. So I got the flow constants here, and I just define them as the square root of y and 2 over y. And remember, this y is the level. So the flow is not linear. And I'm also assuming that the tank sides are not constant. The area of tank 2 I've assumed is just a constant 1 meter squared, but the area of tank 1 is changes with the elevation. And I can put any equation I want to in here, and I'll be able to solve that later. You'll be able to see how I solve it. So now I need to choose a closed loop time constant, and I'm going to choose a closed loop time constant of a half a minute, 30 seconds, and there's some limits to how large I can make that based on these equations up here. It's possible that I could get some negative gains if I make the time constant too big. So I have to choose a reasonable range for my closed loop time constant. This is the initial level for the first tank, the initial level for the second tank, and the initial set point for the first tank. Now, here is where I get fancy and I start to geek out. I have the gain, the open loop gain and time constants for the first and second tank, and I use the equations from above, from the differential equations, but now instead of being a constant, the flow constant is a function of the level, and also the area is a function of the level. So what I'm doing is that every second I'm updating the open loop parameters for the gain and time constant for both the tank 1 and tank 2. Then using that function I defined above, I'm changing the gains for the controller gains for this is the proportional gain for the controller for tank 1, this is the proportional gain for the controller for tank 2, and this is the integrator time constant for tank 2. So I'm updating the controller gains on the fly as a function of level. So now I calculate the flow into the pump, and that's basically very simple. I have the set point for tank 1 and the level of tank 1. I subtract the 2, and I just multiply it by the proportional gain or the controller gain here, and I just limit the flow. I make sure I don't get a negative flow, and I limit it to a maximum of 2 cubic meters per minute, and that makes it so that, well, I've got a pump flow that I can use in the equations here. And then I use the differential equations from above, but again, instead of making using constants, I'm making it so that all the coefficients are functions of the level. So this is the differential equation from above, but all the instead of having constants, I have functions, and that calculates the rate of change in the level for tank 1, and this calculates the rate of change in the level for tank 2 using the equation above. But I've added this disturbance function, which you will see how that comes into effect a little bit later. Then I have to calculate the set point. The tank number 2, its PID, or actually I minus P controller, is calculating out a set point for tank 1. So this is the proportional gain. Basically, this times this is the integrator gain, and this times this is the proportional gain. And that's multiplied by the error in the set point for the tank 2, and this is the level for tank 2, so that's the error. And this is the rate of change of error. And because I'm using an incremental I minus P controller, I only need to know the rate of change of error, or the rate of change in level for tank 2. This is just limiting. I got to make sure that I don't calculate out a rate of change which would cause the set points to go beyond my level, my 5 meter height limit for my tank, and I got to make sure it doesn't go down below 0, because I can't have a set point below 0 level in my tank. And I return the rate of change of the level for tank 1, the rate of change in level for tank 2, and the rate of change in the set point for the for tank 1. And next I use a Runge-Kutta function. Now, MathCAD has a built-in Runge-Kutta 4 program, but I decided to write my own because I want to just show how simple it is to do the simulation. So what it's calculating here is 4 estimates for every period, and then it's taking an average, a weighted average of those 4 estimates to calculate the level or the state at the next state. And I'm using this function up here, this function f of t. Kind of scrolling too far. I'm using that function f of t to calculate or update my states in my Runge-Kutta function. So now I have to calculate the pump function, and again I've got the state. This is, in this case, y is not the level; it's the state. So I got the level for tank 1, the level for tank 2, and the set point for tank 1. And again, I update my controller gains. I update the my open loop gains. I update my controller gains, and then I figure out the pump flow, which is just the controller gain for tank 1 times the error, and again I limit it to 2 gallons per minute. So here you can see the response, and even though this system is very nonlinear, I get a nice exponential response. It doesn't overshoot here, mostly because we're not saturating. It's possible that a Butterworth filter or a Butterworth coefficients will overshoot, but because the time constants are relatively slow, there is no overshoot. But notice there is a huge error in the difference between the set point on tank 1, which is this blue, and the level for tank 1, which is the red. Huge error. But it doesn't make any difference because, again, the set point for tank 2 here and the level for tank 2 come up and they match, and then I change the level. And here, because we overshoot here, we kind of wind up the integrator a little bit. I didn't do anything to take care of the integrator windup in this example, but you can see it winds up a little bit, and then I get myself back into the set point quite nicely. At time 14 minutes, I add 0.2 meters per minute, cubic meters per minute of water or fluid to the tank, and up into about 15 minutes. And you can see how the system responds. You can see the level goes up for tank 2, and then it goes back down, and then it gets right into the set point again. So the tank level control is very good, and mostly even though we have lots of non-linearities, and even with disturbances, the response is very good. So why bother with all this? Well, I wanted to make a couple points. One is, when you go to college, you can learn how to twiddle gains, and you're just kind of learning how to use the tool. And the people that do the integration or the setup of the system, that's what they're going to probably do. But if you're going to school, you want to go to school to become a designer. And one of the things that you need to be able to do is have specifications, and then you've got to be able to do a simulation to make sure your system's going to meet the simulations, or the specifications. So you need to know, well, how high does the tank need to be? If you don't have the tank high enough, for instance, if we only had this tank 1, if it was only made 2 meters high, we would be overflowing the tank, and that wouldn't be good. What if we needed more pump flow? So someone has to do the simulations and all the math to make sure that the system is going to work. And then you need to be able to run it under typical situations, which I just made this up, but you would need to get some typical historical data to run through your simulation to make sure that the system was always going to work right. So that's the purpose of knowing how to do the differential equations up above. The whole reason is that when you're doing state space, or if you're just doing Laplace transforms, you really cannot handle nonlinear systems very well, whereas if you express everything in differential equations, it's not that difficult to get numerical solutions using the Runge-Kutta, and it gives you just a lot more flexibility on how you're going to do simulations, and allows you to catch more extreme cases in your simulation. So I hope you find this video useful, and you've probably noticed by now that I really do like differential equations a lot better than just state space or Laplace transforms, even though I think they have their place. But in the final analysis, simulations have to be done using Runge-Kutta. Bye.